Okay, this is part 4 video for lesson 8.13, arc length of a smooth planar curve, distance traveled for the AP Calculus BC curriculum. All right. In this video, we're going to use to find examples to find distance using complicated examples where we're going to need a calculator to actually calculate the distance. Won't be easy to integrate, but we can use the calculator. Let's start by finding the arc length of the curve f of x equals ln x from x equals 1 to 8. I like to start by sketching a graph, get a good idea of what it is we're looking for. And we know the graph of ln x looks like this. And we know it intersects the x-axis at 1. And in this case, we are going to look for where x equals 8. So the arc length, this part of the curve, is what we want to measure. If there was a particle moving along this curve from x equals 1 to x equals 8 or t equals 1 to 8, then this would be the distance traveled. So we know from the previous videos that the arc length formula is the integral from, in this case, 1 to 8 of the square root of 1 plus dy over dx squared times dx. And we also know the derivative of ln x, dy dx here, is equal to 1 over x. So we can set up the integral as from 1 to 8, square root 1 plus 1 over x squared times dx. If we type that in the calculator, we're using the TI-84, so we know that when we hit Math 9, it gives us a box for the lower limit, a box for the upper limit, a box for the integrand, and then it'll give us one more box for the variable of integration that we have to fill in. So we're going to fill these in with 1 to 8, and then 1 plus 1 over x squared, like this. Then x is the variable we're integrating with respect to. And my calculator on my computer has an old operating system. It doesn't show this. And it's kind of down right now anyway. So what we're going to do is I've already typed that in the calculator. And the calculator gives us 7.404 or 7.405 if you round it. I like to chop because we don't make errors when we just chop 3 decimals. And so that's the answer on this one. Let's go to the second example. We're going to find the arc length of the curve y equals sine x from 0 to pi. So we know that the graph of sine x intersects the x-axis at 0 and pi. And so here, again, the arc length of the curve is going to be the integral, in this case from 0 to pi, of the square root 1 plus dy over dx squared times dx. We know the derivative of sine x, dy over dx, is equal to cosine x. So we enter in the calculator integral from 0 to pi, square root of 1 plus cosine squared x. Now remember in the calculator, I'll show you in a minute what the calculator syntax will look like for that, times dx. In our calculator, opens up the box when you do math 9, from lower limit, upper limit, integrand, and then a box for the variable of integration. So we're going to type in there 0 to pi 1 plus, and when you type cosine squared x in the calculator, it gives you cosine, opens up parentheses, you put in the x, close parentheses, then you square that. This is the calculator syntax. And dx, put in the variable of integration, and this time when we do that, we end up with, calculator tells us 3.820, or just 3.820, because if we round this one, it rounds down. If this was a context problem where you had a particle moving along the curve, you would want to put whatever appropriate units in there if you were doing this on an FRQ. And let's find one more. This time it's a little more interesting. We're going to find the length of the boundary of the region bound by the y-axis, the curve f of x equals ln x plus 1, and the curve y equals 3. Let's sketch this graph, get an idea of what we're looking for. And we know that ln x plus 1 is the curve of ln x shifted 1 units to the left. So instead of intersecting at 1, it's going to intersect at 0. If it's the curve y equals 3, that means it's going to intersect when y equals 3. If we set ln x plus 1 equal to 3, that becomes e to the third equals x plus 1. So x value, where the intersection occurs, is e to the third minus 1. And of course, this part of the region is bounded just 3 units long. And so what we have is this part of the curve 3, and then this part of the curve is e to the third minus 1. So what we need to find is the arc length of the curve, ln x plus 1, equals 3. Again, the arc length is the integral from 0 here to e to the third minus 1 of the square root 1 plus dy over dx squared times dx. We know dy dx of ln x plus 1 is 1 over what's inside the ln times the derivative of what's inside the ln, which in this case is just 1, so that makes it nice and easy. So we're going to take that squared. So we're going to have, this is going to be the integral from 0 to e to the third minus 1 times the square root of 1 plus 1 over x plus 1 squared times dx. That's just the curve that we're looking for here. Okay? And so that's going to be this plus 3 plus the e to the third minus 1. That's going to make up the boundary, the length of the boundary of the region. When I enter this in the calculator, Math 9 gives me the box here for the lower limit, box here for the upper limit, box here for the integrand, and box here for the variable of integration. So I'm going to type those in as 0, e to the third minus 1, then square root 1 plus, sorry about that, 1 over x plus 1 squared, and then dx. Then I'm going to add 3 plus e to the third minus 1, or you could add 2 plus e to the third. This is the expression I'm going to type in my calculator now. So math 9, lower limit 0, upper limit e to the third minus 1. Double check, make sure that your calculator, everything's entered the way you want it. Inside the integrand there is the square root of 1 plus, now I'm going to let's do the fraction thing here. This is going to be, whoops. Math 9, 0 to e to the third minus 1. Then the square root. 1 plus, now I'm going to put open parentheses and then do my fraction thing. It's going to be 1 divided by x plus 1, close parentheses squared, and times dx, and the x. Then I'm going to do, just going to change this to plus 2 plus e to the third. And the calculator is going to give me a figure, and it gives me 41.613 units. And again, if you had a contextual problem, you would want to put the appropriate units there. But that's how we're going to do these find the arc length for 8.13. Final video.